Jai Hind everyone. This is once again Navjyoti Sharma taking another lecture on analysis of single phase AC circuits. In the first phase of analysis of single phase AC circuits, we have seen the behavior of purely resistive, purely inductive and purely capacitive circuit, and we have also seen the three kinds of powers, the reactive, the apparent and the true power for an RL series circuit, right? If that is so, continuing on, the power triangle what we have discussed, right? The having the three powers, the active, reactive and apparent power, right? That can be given as, if at all I see, right? This is the voltage, the current. So, the horizontal axis will be having the true power P, which is given by VI cos phi, right? The reactive power Q, and the resultant, the phasor addition of these two will give me the apparent power S given by VI. So, the power factor is having another formulation, right? That formulation can be given as, the power factor can also be given in terms of the ratio of the two powers, that is true power by apparent power, that is VI cos phi by VI, or in symbolic representation I may be giving it as P upon S, right? Now, just take an example for an RL series circuit. So, given if V voltage is given by 200 sin 377t and current is given by 8 sin 377t minus 30 amperes for an AC circuit, then determine the power factor, the true power, the apparent power and the reactive power. If that is so, if we just see, voltage is given as 200 sin 377t and the current is given as 8 sin 377t minus 30, right? So, I can be having the maximum value of voltage and current, that is 200 and 8 amperes. Once again, the RMS value, we know the relationship between the voltage, the RMS value and the maximum value. So, maximum by root 2 will give me the RMS. So, the RMS value of the voltage is 141.42, the RMS value of the current would be 5.656, right? What is the phase of voltage? The phase of the voltage, that is 200 sin 377t. So, the phase of the voltage is just 0. So, how could I write the voltage in phasor, or I must say in polar form, right? R angle phi form. R represents the magnitude. So, the magnitude RMS value, that is 141.42 with its phase. Phase is 0. Similarly, current. The RMS value of the current 5.65 with its phase. If you just see the expression, what is its phase? The phase is minus 30. So, with the phase minus 30. If that is so, now what is the power factor? The angle between voltage and current, voltage is having the angle of 0 and the current is having the angle of 30. So, the power factor is given by cos of 30, that is 0.866. Why lagging? Obviously, the current is lagging the voltage. If the current is lagging the voltage, the power factor will be lagging. It's an RL series circuit, right? Apparent power given by VI, S 800 volts, volt ampere, voltage is 141 and current is 5.65, multiplying that I will be having 800. True power is given by VI cos phi, 800, it is already VI multiplied by the power factor 0.866, that much of 269.8 watts. Then finally, the reactive power VI sin phi, VI is once again 800, sin of 30 will give me 400 volt ampere reactive, VAR. Moving on with the RC series circuit. Right. Now, in this case, RC series circuit, if at all I see, once again, the voltage given is sinusoidal, right? But the two components are in series, so the voltage will get divided. The voltage across the resistor is VR and the voltage across the capacitor is VC. The current is same. Once again, going with the phasor diagram and determining the value. The component which is common, or the element which is common to both the R and C, that is the quantity which is common to R and C, that is current. So, I will take current as the reference. What about VR? How to place VR? VR must be in phase with current, right? So, that is in phase with current VR. VC for a purely capacitive circuit, what we have learnt? For a purely capacitive circuit, the current will lead the voltage by 90 degree for a purely capacitive circuit. Current should lead, that means the voltage should lag, right? So, I will make VC downwards, lagging the current by 90 degree minus VC, and this gives me the resultant. Then So I may be saying that V is equals to the phasor addition, that is VR square plus VC square under root. Once again, VR is equals to I into R whole square, I into XC whole square, right? Or I is equals to under root of R square plus XC square, where this R square plus XC squares gives me what under root? That gives me impedance of the circuit, right? Impedance of the circuit. If at all you just see, V is equals to I into Z. So for a RC series circuit, the impedance of the circuit is given by under root of R square plus XC square. Now, if at all I see, how does it behave? So if this is the voltage, right? If this is the voltage, the important thing in this curve to notice is, if this is the supply volt current and this is the supply voltage, now in this case, the current is leading the voltage not by 90 degree, but with certain angle phi, right? So supposingly I say that this V is equals to some Vm sine omega t. So what should be the expression for the current? Obviously, this is leading the voltage by 90 degree with an angle phi. So I must write it as Im sine omega t plus phi, right? If that is so, right, both of these can be given. If this is my reference voltage, so the current that will initiate, right, by 5 degrees earlier. So that will be starting, or that will be leading, the current would be leading by an angle phi. Now coming to RLC series circuit, right? Now if at R, L and C, all the three are connected in series, how the circuit will behave? Now if that is so, once again it's a series circuit, so the voltages will get divided. Across R I'll be having VR, across L I'll be having VL, across C I'll be having VC, and the current is remaining same. If that is so, in this case, once again I'll be going with the phasor diagram to determine what will be the relationship between voltage and current. If that is so, current, once again the reference phasor, VR on the same axis, being in same phase, right? Then here this is VL minus VC, considering that VL is greater than VC, right? Why? The VL would be represented upward and VC must be represented downwards. But both of them are in phase opposition. If that is so, the resultant would be given by which one is greater. So if at all I consider that VL is greater than VC, right, which may be opposite, right, in the another case. So if at all I just consider that VL is greater than VC, then the resultant will be VL minus VC towards VL side. And the resultant would be given by the phasor addition of VR and VL minus VC. So I may be giving V is equals to under root VR square plus VL minus VC whole square. Substituting for VR, substituting for VL, substituting for VC, I'll be having V is equals to I into under root R square plus XL minus XC whole square. What is this once again? I into Z. So for a purely, for an RLC series circuit, the impedance offered by the circuit is given by under root R square plus XL minus XC whole square. And this is the magnitude of it, right? How can I give the power factor? Can I give the power factor of the circuit as well? The power factor of the circuit cos phi in terms of R and Z can be given as R by Z, where Z is given by, once again, under root of R square plus XL minus XC whole square. There can be three cases in this particular case, right? What can be the three cases as we were discussing? One can be when VL is greater than VC, what we have just seen. Another can be when VC is greater than VL. In that case, obviously the resultant will not be on the positive imaginary axis, it will be towards the negative imaginary axis, and that would be VC minus VL. And the third case, if both of them are equal, if VC is equals to VL, in that case, both of these are equal and opposite will cancel out each other, and I'll be just remaining with VR. So the circuit will behave purely resistive. This is the tabular table which represents all the kinds of load having purely resistive, inductive, capacitive, RL, RC and series RLC, their polar and rectangular representations, right? What will be the power factors what we have seen? Likewise, purely resistive is having 0, the angles 90, minus 90, similarly the power factor, right? And the nature. Likewise, if it is 0 for a purely inductive, we used to call it as 0 lagging. 0 leading for purely capacitive. Similarly, if it is an RL circuit, it is lagging power factor, lagging but not by exactly 90 degrees but with certain angle phi. Similarly, leading, the current is leading the voltage by certain angle phi. Let us go on with the numerical. Say a series RLC circuit is composed of 100 ohms resistance, 1 Henry inductance and 5 microfarad capacitance. A voltage of Vt is equals to 141.4 cos 377t volts is applied to the circuit. Determine the current and voltage VR, VL and VC, that is the voltage across resistance, inductance and capacitance. Okay. So, the voltage being given is 141.4 cos 377t, right? Cos can be converted into sine to have everything uniform. I will be converting every waveform into sine. So, converting cos into sine, I will be having sine 377t plus 90 degree, right? So, the maximum voltage is 141.4, fine. Now, omega, that is 377, it was given as omega t as 377t. So, I am getting omega as 377 radians per second. The RMS value of the voltage, that will be given by Vm by root 2, that is nothing but 141.4 upon root 2, that is 99.84 or nearly 100. So, in the polar form, I can represent the voltage with magnitude. Magnitude is 100. With its angle, what is its angle? Angle is 90, right? Now, what about ZL, right? Or the total impedance if at all, I directly go with. What is the total impedance? So, for a series RLC circuit, right, the impedance in rectangular form can be given as R plus or minus J XL difference XC. This is in rectangular form. Am I correct? Right? This depends whether XL is greater or XC is greater. So, let us find what is XL. So, XL if at all I just find it off, that is 377 angle 90 degrees, right? XC, that is going to be 1 upon, or this is 530.50 ohms. This is XC, this is XL. So, if at all you just see here, which one is greater? XC is greater. That means, in this particular case, the expression has to be R minus J XC minus XL, right? So, what is R? Resistance is 100 minus J 530 minus 377, that is 153.5. Converting this into its polar form to have the magnitude, the value would be 183.2 with an angle of minus 56.91 ohms. So, this is the total impedance of the circuit. Once we got the total impedance, I can have the current given by voltage upon total impedance. Voltage is 100 with an angle of 90, and then impedance we just got. Substituting that, the current would be 0.54 with an angle of 146.917. 90 minus of minus 56.9177. So, these angles would be added. So, this will be given as 146.9177. Now, what is the voltage across resistor? I into R. Current 0.5454 with an angle 146.911. Resistor, it's R, purely resistive, that is R with an angle of 0, 100 with an angle of 0. That gets me 54.58 with an angle of 146.9177 as the voltage across the resistance and the current would be in same phase. What is the phase of the current? The phase of the current is 146.911. So, that must be the phase of VR and we are getting it. What is the phase? 146.9177. VL, I into XL, 0.54, this is the current. XL or ZL, that can be given as XL angle 90 plus JXL. So, 377 with an angle 90, that gets me 205.76 with an angle of 236.91. Lastly, VC, I into ZC or XC, 0.5458 and XC is given by 530 286.5 with an angle of minus JXC, that means minus 90, right? So the answer is 286.54 with an angle of minus 50, with an angle of 56.9177. In case of multiplication of the polar quantities, the angles would be added algebraically as per their signs. Whereas in case of divisions, numerator angle minus denominator angle with their symbols. Now continuing on with the parallel AC circuits. For solving the parallel AC circuits, they can be solved using two methods. One is by phasor algebra method, another one is the admittance method. The phasor algebra, if we just see, say, I am having a parallel circuit where an R and C is connected in series and this combination is in parallel with R and L, right? Supplied with a common voltage V. In parallel circuits, the voltage remains same, but the current is getting divided in I1 and I2. Fine. If that is so, I can write Z1 as some Z1 with an angle of minus phi1. Why this is so? Because this is an RC circuit. The impedance will have negative angle, where the magnitude of Z1 is given by under root of R1 square plus XC1 square. And the angle phi1, this phi1 is given by tan inverse XC1 by R1. Similarly, Z2, that means for this circuit, once again Z2 with a positive angle of phi. Why? Because this is an RL circuit. If that is so, the magnitude of Z is given by under root of R2 square plus XL whole square, and the angle is given by tan inverse XL by R2. Now this becomes very easy, right? This is a parallel circuit. I can directly, both of these are directly parallel and supplied across a common voltage. If that is so, the current can be given as V upon Z1, voltage V angle 0, impedance we have already calculated, Z1 with an angle of minus phi1. So the currents can be calculated. Similarly, I2 would be given by V upon Z2. Definitely the addition of I1 and I2 is going to get me the total current, right? This is a parallel circuit, addition of these two, but the phasor addition of I1 and I2 is going to get me the total current, not only the magnitudes. Another method, what we are calling it as admittance method. Now just see what is this admittance. So the admittance of an AC circuit, it is defined as the reciprocal of impedance Z, right? The unit of admittance, that is Siemens or mho. When the impedance Z is in opposition to the alternating current flow, then the admittance is the inducement of the alternating current flow, right? What are the components of this admittance? The components of this admittance are conductance, which is given as G given by 1 upon R. It is the reciprocal of resistance, right? Then susceptance. It can be once again inductive, it can be capacitive, right? If it is inductive, I used to call it as BL 1 upon XL. If it is capacitive, I used to call it as BC 1 upon XC, right? The units, if at all I say, admittance is given by G plus or minus JB. If it is plus, then this will be C. If it is minus, it will be L, right? Now, if R and L are in parallel, in this case, I can be calculating the admittance as, if at all I just go with this, the current that is given by V upon Z, I1, if at all I see here, I1 would be given as, both of these are connected across V. So, I1 is given by V upon R. I2 is given as V upon XL. If that is so, addition of these two are going to get me the total current. Total current given by V upon Z. So, V upon R plus of minus J V upon XL. That is 1 upon R minus J 1 upon XL. So, I may be saying 1 upon Z is nothing but Y. 1 upon R, that is giving me G, the conductance, and 1 upon XL is giving me susceptance, that too inductive susceptance. So, Y in total gets me G minus JBL, conductance minus J of inductive susceptance. Similarly, if at all I go with RC, the same calculation if at all I get for I1, then for I2, adding both of these. This time I will be getting admittance to be equals to G plus JBC, capacitive susceptance. Taking an example, say a resistance of 20 ohms and a coil of inductance 31.8 millihenry and negligible resistance are connected in parallel across 230 volts, 50 hertz AC supply. Find the line current, the power factor and the power consumed by the circuit. Now, this is a parallel circuit having a resistor and inductor in parallel. If that is so, obviously, IR, the current in the resistive branch, that can be given by V upon R. Both of these are having the common voltage, that is V. So, V upon R, that is 230 upon 20, giving me 11.5 amperes, that is in phase with voltage. Similarly, XL 2 pi FL or omega L, considering the frequency, it is given to be as 50 hertz. So, that is 2 pi 50 into L. L is given to be as 31.8 millihenry, 10 to the power of minus 3. Substituting, I will be having it as 10 ohms. So, the current in the inductive branch, that means IL, that will be given by V upon XL, which we have just calculated. V upon XL, that means 230 upon 10, that is 23 amperes, but this is lagging the voltage by 90 degree, right? So, now the line current, the total current which is flowing in the circuit must be the phasor addition of both IR and IL. That means under root, the magnitude would be given by under root IR square plus IL square. Going for it, 11.5 square plus 23 square under root, I will be having 25.71 amperes. What will be the power factor? The power factor can be given as the angle between the total voltage and the current, or I may be giving it as the ratio of IR upon I. 11.5 upon 25.71, that is 0.447 lagging. And the power consumed, that means whenever it is being asked the power consumed, we are asking about the actual power consumed by the circuit. That is the active power, the real power, the true power, that is given by VI cos phi 230 into 27.51 into the power factor, we got it as 0.447, that gets me 2643 watts. Thank you all for listening me so patiently. Thank you.